times the strain tensor, but now this is written as a vector and a matrix, and we just write it as a column. I guess you can imagine now that if we have a vector here and a vector there, what goes in between is a matrix, right? But if you have a matrix 3 by 3 and a matrix 3 by 3, in this case, what is going to go in between? Can you write that in paper? You cannot, because that's going to be like a matrix in 4 dimensions. And you cannot write in paper 4 dimensions. So that's why we use this other type of notation. So we can write that as a matrix in paper. And again, this is called void notation. And basically, what you do simply is you convert this into a vector. And this is a matrix. And now this is a vector. We just do that for simplicity. But it's exactly the same thing. And notice also we take advantage of the symmetry of the strain tensor and stress tensor, so we don't write epsilon 2,1, epsilon 3,1, and epsilon 3,2 because we know that those are the same. One more thing over here. This matrix actually has a name, and it's called this entire thing, and this D is called a compliance matrix. And we're going to see the opposite of that compliance matrix now. Yes?
So the reason that there's no strain in like epsilon 1, 2 is because they're like in the first column stress 1, 1 does it usually acts perpendicular, right? Is that why it's 0?
These zeros over here?
Yeah, let's just look at that first 0 in epsilon 1, 2.
That one?
No. The 2.
This one?
Yeah, yes.
Yeah. What this one means is when we do matrix multiplication, we'll do this one times that one, plus this one times that one, and so on, right? So what that 0 means is that this sigma 1, 1 cannot produce any shear strain epsilon 1, 2. This sigma 2, 2 cannot produce any shear strain epsilon 1, 2. Nor this one, nor this one and that one. The only one that can produce a shear strain epsilon 1, 2 is sigma 1, 2.
But what's the physical reason behind sigma 1, 1 not producing that strain in epsilon, that first slide?
The physical reason for that would be that if you look at this schematic, a normal stress would not be able to, because it's normal to that phase, would not be able to distort the shape of this
like
in shear strain, like you know, like this.
Okay. Because it has to be perpendicular, is that right? In
order to have this deformation like this, you need to have a shear stress, and if you don't have a shear stress, you cannot distort the angles. You're just going to produce a volumetric strain.
It has to be in the same direction.
And that's something which is called decoupling between shear and normal strains. But you get into a good point. Actually, this is a simplification we do. There are some materials in which actually you do produce sometimes shear strain by changing the normal stress. And that happens sometimes in sand, where, you know, we're going to get to this later on, but imagine that you have grain of sand locked in like this, okay? So when you move, so my phase is one grain of sand, the other one is the normal. When you move this one in shear like that, from here to there, as it rolls over, you do produce a strain in this direction because the sand dilates. But in linear elasticity, we don't take that into account, okay? We're halfway of our derivation. Let me see where. Oh, so we were over here. We wrote now this general relation of elasticity in 3 dimensions with this matrix. And we said that now we can relate strains to stresses. The inverse of this relationship would be to express now stress as a function of strains. And in this case, this one is called stiffness matrix. How am I going to get C? If I know what D is, how would you get C out of here? 1 over D, but you have to be careful, because when you deal with vectors and matrices, it's not really 1 over, but it's going to be the inverse of C. And the inverse of C, you can check this. You go to Wolfram Alpha and you do the inverse of this, and it's going to get you what I'm going to write. Okay, but we're not going to go through that because that's going to be a lot of work to do an inverse of a matrix here. So I'm just going to put straight the result, and this is going to look something like this. It's going to be, again, another matrix. And there's going to be a common factor. I'm going to take it out of the matrix, which is going to be this one.
Is that supposed to be D to the negative
D,
one?
negative 1.
Thank you very much. D, yes. All right, so now we have this new matrix that is the inverse of the previous one, and it looks like this. Similar as the other one, you have zeros in here. And now here we have 1 minus 2 Poisson ratio divided by 2. And these are zeros. It's the same thing, okay? But it's just inverse of the previous matrix. I like to divide this matrix in 4 parts and these vectors in 2 parts. So notice that here I have normal stresses, shear stresses, linear strains, and shear strains. But it is just the inverse of the previous one. Okay, so how now is this useful? Yes, sir.
Do we have a row of zeros there in the bottom left?
Bottom, oh yes, 0, 0. Okay, so what do we do with this? We use these matrices in order, and these equations in order to compute now problems that are not just in 1 dimension, but may involve 3 dimensions. Because now we have all the equations that we need in there to solve problems a little bit more complex than the one that we did before. For example, the problem that we're going to solve now is something which is called a uniaxial strain path. A uniaxial strain stress path. Let me tell you what that means. Imagine that, again, one more time, we go to Galveston, in which by now we know that there are muddy sediments, right? Make the water look a little bit brown. And here, in Galveston, and here I'm offshore, and throughout the length of geological time, we see how sediments get to the seafloor, and they may make layers of sediments with time. I'm going to assume that there are no tectonic, important tectonic movements in this region, so that I don't have additional forces in horizontal direction. So you could, I hope you can see that the sediments, as they travel from here with time, they get buried, and as they get buried, they change size, but mostly just in vertical direction. So most of the compaction takes place in one direction. Let's say in this case I put a coordinate system which is, let me see, 1, 2, and 3. So my assumption is that the strains in direction 1 is equal to the strain in direction 2, and those are equal to 0. But the strain in direction 3 is not equal to 0. That's what happened in these cases. That's something which is called, again, is called the uniaxial-strain stress path, because there is just change of strain in one direction. And further, I'm going to say that all the shear stresses are equal to 0. Let's see what is going to be the effect of assuming these more realistic subsurface conditions into the relationship between stress and strain. Okay, so first of all, let's see, strains equal to 0 are going to mean that if these are 0, all of these are 0. So I'm not going to write them, okay? And I'm just going to concentrate on the top. And if I do that, then I'm going to have sigma 1, 1, sigma 2, 2, sigma 3, 3. It's going to be equal to what I have above times 1 minus Poisson ratio, and here Poisson ratio. Now times, what is epsilon 1, 1 in our current case? It's going to be 0. Epsilon 2, 2 is going to be 0. And epsilon 3, 3 is going to be different than 0, right? Okay, so let's see what I can get from these equations. First of all, let's do the easy one. What is going to be now as an equation, single equation, sigma 3, 3? If you were to multiply now, sigma 3, 3 will be the result of, it's going to be the third row dot product this, right? So notice that these are zeros, so these two are not going to get into the equation. Just going to be simply this number times that number times that, right? And this is going to be equal to this divided by that times epsilon 3, 3. Note something which is very important here. This is an equation that relates stress to strain, right? But you could tell me, oh, but you already had an equation that was relating stress to strain. And that equation was this one, you see? So let me put those two together. I have an equation that tells me what is stress as a function of strain, and I have another one different that tells me what is stress as a function of strain. What is the difference between these two?
One is
coefficient.
Exactly right. This one over here is unconfined. This one over here is confined on the sides. It all is the same thing, but it just varies depending on your boundary conditions. Our boundary conditions here are different. Here we're letting this solid expand to the sides. In this case, we're not letting the solid expand to the sides. Actually, if I were to draw the deformed configuration of this one, it would be something like this, in which there is no strain in this direction. This is sigma 3,3, there is epsilon 3,3, but there is no strain in the other direction. And now, this coefficient goes by the letter M, and it's called constraint modulus. And notice that it's a combination of Young modulus and Poisson ratio. Just try to make sense out of this without doing any numbers. Which one do you think is going to be bigger, M or E? E. Why is E going to be bigger than M?
Because M is a fraction of E.
Allows for more strain.
So let's do this as an experiment. This is going to be E. E is letting it expand to the other direction. Well, in order to get M, I need to get to the same deformation in this direction, but now I'm going to have constrained these sides. So I'm going to have to constrain this side, and I'm going to have to push a lot more to get into that direction. So M is actually going to be bigger than E, because let's see if we can get this. I'm trying to let the node expand. If I were to let it expand, it will deform even more in this direction, in the axial direction. When you compress in this direction and you do not let the solid expand, actually you need more stress to get to the same level of strain. That's why M is always larger